Welcome to Theory of Computation. This is lecture number 29. In the last lecture, we were able to finish the proof of the celebrated Cook-Levin theorem. As you must remember, the Cook-Levin theorem talks about one particular problem in the class NP. It talks about one concrete problem in the class NP, and it says that that problem's satisfiability is NP complete. What I want to do is today talk a little bit about the meaning of what it means for a problem to be NP complete. What does it tell us about it? Well, let us first look at this theorem and review the definition of NP completeness, and then we would like to know what have we actually done and what are the possible consequences of proving this theorem, and what does it really mean when we say that a problem is NP complete. So we finished the proof of the Cook-Levin theorem, and the theorem states that SAT is NP complete. What this means is that SAT is in the class NP. That means it itself has a polynomial time verification algorithm. And that was not the hard part of the proof. The bulk of the proof was to prove the second part, which says that every problem in NP is polynomial time reducible to SAT. Well, one way we can view this theorem is by a picture. In this picture, you see I have shown the class NP by a big circle, and the little circles over there denote problems which belong to the class NP. And what I have done is put SAT on top of it and drawn arrows from these little circles. This depicts, the arrow depicts polynomial time reducibility, and this picture shows that everything in NP can be reduced to this one problem that we call SAT. So, in that sense, we have proved that SAT is an extremely general problem. Any problem that has a polynomial time verification algorithm can be reduced to SAT in polynomial time. Now, let's think about what this really means. And what do we really mean when we say that a problem is NP complete? Remember our previous goal in computer science. When we look at a computational problem, what do we try to do? We try to find algorithms that solve these computational problems. This whole idea is abstracted in terms of languages in this course. So every language is a computational problem. And in computer science, what we do is we try to find an algorithm that would solve that problem. But if we just find an algorithm and the algorithm takes a lot of resources, then that algorithm is not practical. So complexity theory comes in and says that, well, the notion of practicality is loosely captured by polynomial time, at least in terms of time. So when we get a computational problem, it's not enough to find an algorithm that solves that problem, but what we want is an efficient, a polynomial time algorithm that solves that problem. Well, once we have this notion, then we came up with a notion of this class called NP. As we will see as we start looking at problems which are in the class NP, and you have seen that there are a lot of problems which are in the class NP, we would realize that this somehow is our wish list. These are the problems that we want to solve in polynomial time. And this wish list is just what we would want, what we think we should be able to solve. So it's not a very ambitious wish list. If somebody were to come and say, well, I want to solve the halting problem in polynomial time, of course they're being over ambitious, because the halting problem is too difficult. It's not even computable. It's not even decidable. We don't even have an algorithm. There is no algorithm to solve the halting problem. So the question of solving it in polynomial time is out of the question. On the other hand, NP seems to be a really nice class of problems that we would want to solve in polynomial time. Well, when we start looking for algorithms for some of the problems in NP, we realize that people have worked for many years and they've not been able to solve many of those problems. So the question arises, is there something intrinsically hard about these problems? Maybe we're looking for a polynomial time algorithm for problems which don't have a polynomial time algorithm? Well, in that case, as theorists and as mathematicians and theoretical computer scientists, we just don't want to give up. If we give up, then that would not be a scientific approach. If we come across a difficult problem, what we want to do is either solve it or somehow prove the impossibility of solving it. So, for example, if I were to ask you to write square root of 2 as a ratio of two integers, then either you should show me how to write square root of 2 as a ratio of two integers, or prove to me that it cannot be done. Similarly, for some of the problems in NP, we would want to come up with polynomial time algorithms, and since we have failed for many years, now some scientists would want to prove that for these problems there are no polynomial time algorithms. Well, satisfiability is one of those problems. People have been looking for good algorithms for satisfiability for many years, and they have actually found very nice heuristics which can practically solve many satisfiability questions that arise in real life. However, no one has been able to find a polynomial time algorithm. So in this case, scientists would want to prove that there is no polynomial time algorithm. Unfortunately, we cannot do that, or we have not been able to do that yet. And when I am talking about we here, I mean we as a scientific community. No one in the world has developed the methods and the skills that would answer this question for us. The question is whether there is a polynomial time algorithm for satisfiability or not. Nobody has been able to definitely prove yes or no. This is when the Cook-Levin theorem comes into the picture. The Cook-Levin theorem, what it tells us is that satisfiability is NP-complete. So it tells us that if someone were to find a polynomial time algorithm for satisfiability, they would immediately find a polynomial time algorithm for every problem in NP. Now, this is a very important and very interesting statement. The way I really think about it is that NP completeness of a problem gives us evidence that the problem is hard, that the problem is difficult. In fact, a very famous computer scientist, Jack Edmonds, he made a conjecture which, if read properly and in today's language, it says that satisfiability does not have any polynomial time algorithm. Actually, Jack Edmonds' conjecture is equivalent to saying that the class P is not equal to NP. We have not been able to separate these two classes. We have not been able to give a definitive proof that P is not equal to NP. But when we establish that one problem, a given problem, is NP complete, what we do is we give huge evidence, enormous amount of evidence that the problem is difficult, that for this problem to have a polynomial time algorithm will have amazing consequences. It would imply that P is equal to NP. So, what you need to remember is, if somebody proves that a problem is NP complete, they have neither shown a polynomial time algorithm for it, nor have they shown that the problem cannot be solved by a polynomial time algorithm. What they have done is they have given tremendous amount of evidence that the problem is difficult. And here, if we believe Jack Edmonds' conjecture and mind that it's just a conjecture which says that P is not equal to NP, then modulo that conjecture, keeping that conjecture as believing in that conjecture, what we believe is that these problems will not have polynomial time algorithms. So, if someone says that I have proved a problem to be NP complete, they have given us a lot of evidence that the problem may not have polynomial time algorithm, although the scientific community at this time cannot give any definitive proofs. Well, what use is this theory, you may ask? You may ask, why do people prove that problems are NP-complete? This does not seem to have any kind of application. Well, in computability theory, we were proving that problems are not decidable. So what happens if I were to tell you that a problem is not decidable, or prove to you that a problem is not decidable? Well, in that case, you know that there is no algorithm which will decide that problem. And so you stop looking for algorithms. Once I prove that a problem is not decidable, every scientist in their right mind would stop looking for algorithms for that problem. Similarly, or analogously, if someone proves that a problem is NP-complete, most computer scientists who believe in the P not equal to NP conjecture will abandon looking for polynomial time algorithms for that problem. What does that do? Well, that is a very, very practical approach. If you know that there is enormous amount of evidence that a problem does not have a polynomial time algorithm, then you should not be looking for one, because you can use your time more productively on other things. Well, usually when a problem is proved to be NP-complete, then people abandon looking for polynomial time algorithms for that problem, but they don't abandon working on that problem at all. They start looking for what we call approximation algorithms for that problem, and therefore what they do is they use their time more productively. So in a very loose and informal sense, if somebody proves that a problem is NP-complete, well, you can think of NP-completeness as being computer science-y for saying that a problem is hard. So it's the computer science jargon for saying that the problem is hard. And here I'm using hard in both sense. A, that there is huge evidence that there may not be a polynomial time algorithm for that problem, and therefore the problem is hard. And B, the problem is hard as a challenge to mathematicians and computer scientists, that finding a polynomial time algorithm for it would require some ingenious idea, or proving that there is no polynomial time algorithm will require an ingenious idea which no one has come up with so far. Why am I talking so much about this one problem satisfiability and NP-completeness? Well, because whatever I am saying applies not only to satisfiability, but to many other problems. After Cook and Levin had proved that satisfiability is NP-complete, computer scientists, and especially a very famous scientist, computer scientist, Richard Karp, was able to show that SAT was not one instance, it was not one example of an NP-complete problem, but there are many of them, there are lots of them. And these problems, when you look at them, on the surface, they look very different from each other. Now, let's think about if I tell you that I have two problems, A and B, and they're both NP-complete. Well, this means both of them are in the class NP, and both of them are polynomial time reducible to each other. Now, if two problems are polynomial time reducible to each other, that means that their relative complexity is roughly the same. I can convert one problem into another and the other one into the first problem very quickly. So I can convert the first problem into the other and the other into the first problem. This means that both of these problems in essence are the same. They are disguised in two different dresses. So all NP-complete problems are polynomial time equivalent to one another. What does that mean? Well, that means that all NP-complete problems in some sense, in some essence, are the same problem. Well, once Cook and Levin proved that SAT was NP-complete, computer scientists started finding out that many other problems are NP-complete. Especially, Richard Karp was able to prove a lot of problems which look very different from each other are NP-complete. So all these problems that look very different on the surface in some sense had the same essence. they were equally hard, and they can be transformed from one to another in polynomial time. Nowadays, the number of known NP-complete problems is in thousands. There are problems from various areas. They look very different. There are many problems that come from graph theory that are known to be NP-complete. A lot of problems that come from combinatorial games are known to be NP-complete. Problems from database design, some problems from scheduling are known to be NP-complete. Problems that arise in operating systems such as deadlock detection is known to be NP-complete. Problems concerning set systems are known to be NP-complete. On the surface, all these problems look very different from each other, and it was a big surprise for people to find out that these problems can be transformed from one to the other in polynomial time. So anyone who was trying to find a polynomial time algorithm for one of these problems was implicitly also trying to find a polynomial time algorithm for all the other NP-complete problems, and in fact all the other problems in NP. So people who were working on, say, deadlock detection were implicitly working on another graph theoretic computational problem. People who were working on scheduling problem were in disguise also working on problems that came from combinatorial games. But these people did not know it. These people did not know that they were working on problems which were so general. Once the theory of NP-completeness was established and developed, these people were aware then that they are working on very general, very difficult problems. So the theory of NP-completeness makes us aware that these problems are extremely hard. And once again, I'm using hard in two senses here. One is that there is a lot of evidence that there may not be a polynomial time algorithm for that problem, since the problem is NP-complete, and therefore the problem is computationally hard. The other hard I'm using is in another sense. What I mean is that if somebody is taking up the challenge of working on an NP-complete problem, then it's going to take an ingenious idea to solve that problem, to come up with a polynomial time algorithm. In fact, many people believe that they will never come up with a polynomial time algorithm for that NP-complete problem because such a polynomial time algorithm does not exist. On the other hand, it's going to require an equally ingenious idea to prove that this problem, an NP-complete problem, cannot be solved in polynomial time. So, once again, you should think of NP-complete as being computer science-y for hard. An NP-complete problem is a problem for which we have a huge amount of evidence that the problem is difficult. And once a problem is proved to be NP-complete, most computer scientists stop looking for a polynomial time algorithm for that problem. And this means that they can use their time more productively on other problems, or what sometimes they do is they start looking for what we call approximation algorithms for NP-complete problems. We will look at what approximation algorithms are maybe later in this course, but the point is that when you prove that a problem is NP-complete, you give huge amounts of evidence that the problem is difficult. Now let's try to see what we have done so far, and let's try to prove a few other problems which are NP-complete. So now from Cook-Levin theorem, which says that satisfiability is NP-complete, we would start moving towards other problem, and we will show that some other problems are also NP-complete. So let's start looking at other questions, and let's start proving that they are also NP-complete. An immediate question that would come to our mind is the following once we have proved the Cook-Levin theorem. The question is SAT the only NP-complete problem? Now let's start thinking about this question for a while. So what we want to do is we want to think about what would happen if there was some other problem which were NP-complete. By examining this question, we'll come up with a plan for proving that problems are NP-complete, and this plan would allow us to find an easier route than the one that was followed by Cook and Levin, because we will be able to use Cook and Levin's work, which they have done already, in order to prove that SAT is NP-complete. So let us, for the sake of argument, assume that there is another language, and let us call this language L, and let us say that this language is also NP-complete. Well, the question is, what are the properties that this language will have? This language will have two properties. One, it has to be in NP itself. Suppose we can establish this by giving a verification algorithm. So we'll give a verification algorithm for L and prove that it itself is in NP. The second thing is that all languages L prime in NP would be polynomial time reducible to L. And as you know, satisfiability is a particular language in NP. Therefore, SAT would be polynomial time reducible to L also. So, we know that SAT itself will be polynomial time reducible to this language L. Now, suppose that we have a language L such that it is in NP, and we suspect that L is NP-complete. If this is the case, then SAT is going to be polynomial time reducible to L. And suppose we can also establish this fact. So, we can come up with a reducibility from satisfiability to this new language L. So, what we do is we come up with one reducibility from satisfiability, which is one concrete problem, to this new language L. Then since SAT itself is NP-complete, therefore for any language L prime in NP, we would have L prime is reducible to SAT. So we have two facts, and we'll put them together to obtain a new fact. One of them says that SAT is polynomial time reducible to L. And the second one says that any language L prime in NP is polynomial time reducible to SAT. So we have these facts 1 and 2. Now what happens if we put these two together? If we combine 1 and 2 together, we get that L prime is polynomial time reducible to L. And remember, L prime was an arbitrary language in NP, and therefore this shows that L is also NP-complete. So now we don't have to show that every language L prime is reducible to L in order to show L's NP-completeness. What we will do is we'll just show that SAT is polynomial time reducible to L. Hence, in order to show that L is NP-complete, we only have to do the following two things. We have to give a polynomial time verification algorithm for L, thereby showing that L is in NP. We also have to show that SAT is polynomial time reducible to L, thereby indirectly showing that every language L prime in NP is polynomial time reducible to L. Note that showing that SAT is polynomial time reducible to L is much easier than showing that all languages L prime in NP reduce to L in polynomial time. Thus, we will be using Cook-Levin theorem to establish that the NP-completeness of this new language L. Note, in this case, the scenario is as follows. We have satisfiability, which is already known to be NP-complete. And then we have a language which we want to prove that it's NP-complete, and somehow we use the NP-completeness of satisfiability to make our job easier. What we know is every language in NP is polynomial time reducible to SAT, and since we can reduce SAT to L, therefore every language in NP reduces to L. However, in order to use the Cook-Levin theorem this way, we must prove and understand the following thing about polynomial time reducibility. For this plan to work, we need to recall the following theorem. This theorem says that if A is polynomial time reducible to B and B is polynomial time reducible to C, then we can conclude that A is also polynomial time reducible to C. Thus, polynomial time reducibility is a transitive relation. Remember what a transitive relation is? Well, it's exactly the property that I've written here. If A is polynomial time reducible to B and B is polynomial time reducible to C, then A is polynomial time reducible to C. That property is called transitivity, and polynomial time reducibility happens to have this property. We must understand this in order to be able to make our plan work. The proof of this theorem is so simple that we can revise it in a few minutes. So let's go ahead and do that. Suppose that A is polynomial time reducible to B. Then what does that mean? This means that there is a function mapping from sigma star to sigma star such that x is in A if and only if f of x is in B. The second property that f has is that f can be computed in polynomial time. So it can be computed in order n to the k for some fixed constant k. This is what it means for A to be polynomial time reducible to B. Similarly, B is polynomial time reducible to C. That means there is another function g which maps sigma star to sigma star such that y is in B if and only if g of y is in C. Furthermore, g can be also computed in polynomial time. Therefore, there is some fixed constant L such that g can be computed in order n to the L time. So these are the two things that we know, and that's what we are given. What we want to show is A is polynomial time reducible to C. Well, the candidate function for that is very natural. It is the composition of f and g. That is, you take an input x, you apply f to it, and then you apply g to it. And that should be a reducibility from A to C. Let's see why that is a polynomial time reducibility. To see that A is polynomial time reducible to C, let's consider the following algorithm. On input x, compute y equals f of x, and then compute z equals g of y, and output z. This algorithm computes a function h, which is the composition of f and g, and it is clear that x is in A if and only if f of x is in B, if and only if g of f of x is in C. Therefore, x is in A if and only if h of x is in C. Remember, h of x is g of f of x. The question now is, can we compute h in polynomial time? Let's analyze this algorithm and see how much time it takes. How much time does it take to compute h? So let's take an input and let n be the length of this input. Then it takes order n to the k time to compute y, because it takes time order n to the k to compute f. And it takes order this length of y to the L time to compute z. Thus, the total time taken by this algorithm is order n to the k plus order length of y to the L. Now, we make a very small but important observation, and that observation is that the length of L, the length of y cannot be very long, since f was computed in order n to the k time, so the length of y cannot be longer than order n to the k. Therefore, the length of y is less than or equal to order n to the k, and hence the total time taken is order n to the k plus order n to the k to the L, and you can easily see that the grand total taken by this algorithm is order n to the kl. Therefore, this is a polynomial time algorithm, and thus we can compute h in polynomial time, and therefore A is polynomial time reducible to C. So we have once again convinced ourselves that polynomial time reducibility is a transitive relation. If A can be reduced to B and B can be reduced to C, then A can be reduced to C. Of course, reduced here means reduced in polynomial time. Now, this theorem gives us a plan to prove NP-completeness. Suppose we have a problem K that is known to be NP-complete. So here I've deliberately chosen the name of the problem and made it K. K stands for known. So this is the known problem. We know that this problem is NP-complete. We have one problem we call it k. So, for example, we can take SAT to be k. Right now, we only know one problem, or we have only proved that SAT is NP-complete, so we will take k to be SAT. But as we improve our knowledge, k would be changing. So, we have a known NP-complete problem. Now, suppose we have another problem W that we want to prove is NP-complete. So, here I have called this other problem W for want to prove. So, we want to prove another problem W which is NP-complete. We have a problem K which is known to be NP-complete, and we want to prove another problem W. We want to prove that it's NP-complete. How will we go about doing this? We can proceed as follows. We can show that W is in NP. This is typically easy. We show that W is in NP by giving a verification algorithm for W, and typically this is the easy part of NP-completeness proofs. And what we do is we give a verification algorithm and we show that W is in NP. The second thing we do is we show that K is polynomial time reducible to W. This shows indirectly through transitivity of the polynomial time reducibility relation that all languages in NP are reducible to W. Note that in this case, we don't have to worry about the whole class NP. All we have to do is show that one problem, one known NP-complete problem is reducible to W. We must show that K is polynomial time reducible to W and not the other way around. And this is a point that you must be careful with. To show that W is NP-complete, you must reduce a known NP-complete problem to it. So you must reduce a known NP-complete problem to the problem that you want to prove is NP-complete, not the other way around. W is polynomial time reducible to K is a triviality. Since W is in NP and K is NP-complete, therefore all problems in NP are polynomial time reducible to K. So if you show that W is reducible to K, you have not shown anything. We already knew that, since we knew that K is NP-complete. What you have to show is K is polynomial time reducible to W. This is not a very subtle point. However, I've seen many students making this mistake. When I ask for an NP-completeness proof of a problem W, they quickly give me a reducibility from W to a known NP-complete problem and get a 0 on that homework or exam. So make this very clear that in order to prove that W is NP-complete, you must reduce a known NP-complete problem to it and not the other way around. This will be our basic recipe for showing that other problems are NP-complete. So this recipe will go in 2 steps. We'll show that W is in NP by giving a verification algorithm. And then we'll reduce a known NP-complete problem to W. And this would show that W is NP-complete. Let's follow this recipe by a simple example. Let us start by defining a problem that we will or prove is NP-complete. So now we want to define a problem W that we want to prove is NP-complete. So in order for us to show that this problem is NP-complete, we must first understand the problem and define it properly. This problem is going to be very closely related to SAT. We will call it 3-SAT. In fact, it's going to be a restricted version of SAT. And this problem is going to be important, and we will use it in our proofs maybe once again. So let us say we have Boolean variables x1 up to xn. We will call a variable or its negation a literal. So a literal is a Boolean variable or its negation. So for example, x3 is a literal. x3 bar is also a literal. x5 bar is a literal. x7 is a literal. So a variable or its negation is called a literal. Now suppose we have a lot of literals that are being odd together. We will call that thing a clause. So a clause is taken by taking a lot of literals and combining them by writing an OR between them. So what we're doing is we're looking at Boolean formulas with very special kind of formulas. So let me give you a few examples of clauses. The first example on your screen is x1 or x5 or x7 bar. The second clause is x1 bar or x4 or x6 bar or x8. That's another clause. The third clause is x3 or x5 bar or x11 bar. So I've written down 3 clauses for you. A clause is just an OR of a bunch of literals. Now, a formula in conjunctive normal form, which we will call CNF, CNF stands for conjunctive normal form, is just an AND of a lot of clauses. So, a formula in conjunctive normal form will look like the following formula. x1 or x5 or x7 bar and x1 bar or x4 or x6 bar or x8 and x3 bar or x5 bar or x11 bar. So this is a formula in conjunctive normal form because there are ANDs, and between those ANDs I have just clauses. So if I want to tell you a formula in conjunctive normal form, I'll tell you the clauses of it and then you will AND them together and you'd know the formula. A formula in 3CNF, if all its clauses have exactly 3 literals in it. So formulas which are in 3CNF are very, very simple. They are ANDs of clauses and each clause has 3 literals in it. So let's look at an example of a formula in 3CNF. The first formula is not in 3CNF because if you look at the middle clause, it's x1 bar or x4 or x6 bar or x8. It has 4 literals. This means that this particular clause does not have 3 literals, so this formula is not in 3CNF. On the other hand, the formula written below it is in 3CNF because all the clauses have 3 literals in it. The first clause is x1 or x5 or x7 bar. It has exactly 3 literals. Then that is ended with the second clause, which is x1 bar or x4 or x6 bar, which has exactly 3 literals. And that is ended with the third clause, which is x3 or x5 bar or x11 bar. So a formula in 3CNF is very simple. It has clauses that are ANDed together, and each clause is very simple. It has 3 literals. So the formula looks like this or this or this and 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 all of this. When I was saying this, that has to be a literal. It will be x7 or x5 bar or something like that. So 3CNF formulas are very, very simple. Once we understand what 3CNF formulas are, we can define our language 3SAT. So let us define the following language formally. 3SAT is the set of all encodings of formula phi, so that phi is in 3CNF and phi is satisfiable. So 3SAT is an easier, seems on the surface to be an easier computational problem than satisfiability. In satisfiability, I was giving you an arbitrary Boolean formula and asking you if the formula is satisfiable or not. In 3SAT, I'm giving you a formula which is in 3CNF. So it's a very simple, very special form of formula. And I'm asking you whether this formula is satisfiable or not. Well, it turns out that 3SAT is as difficult as satisfiability if we are talking about polynomial time algorithms. What we will show is that 3SAT is also NP-complete. We want to show that 3SAT is NP-complete, and for that we will follow a recipe. Remember, 3SAT is our new problem, so it takes the place of W in our recipe, and the problem that we know is already NP-complete is SAT, so that takes the place of K in our recipe. So what do we have to do? We have to do 2 things. We have to show that 3SAT is in NP. Well, how will we show that 3SAT is in NP? All we have to do is give a polynomial time verification algorithm for 3SAT. Well, The formal proof of that is left to you as an exercise. I will just hint and say that the same algorithm that we use to verify satisfiability should also work for 3-SAT, since 3-SAT is a special case of satisfiability. So it's extremely easy to see that 3-SAT is an NP. Now, what we will do is do the second step. We will show that satisfiability is polynomial time reducible to 3-SAT. What does it mean for us to reduce satisfiability into 3-SAT? Well, in this case, what we will do is we will start with the formula phi, and we will show how to construct a formula psi in 3CNF such that 1. Psi is in 3CNF, 2. Phi is satisfiable if and only if psi is satisfiable, and 3. Psi can be computed from phi in polynomial time. So what we're doing is, if somebody gives us an arbitrary Boolean formula, what we can do is, by looking at that formula, we can come up with a new formula psi, such that if phi was satisfiable, then psi would be satisfiable. And if phi was not satisfiable, then psi would not be satisfiable. The nice thing about this formula psi is that it would not be arbitrary. It would be in a very special form. It will be in 3CNF. Let's see how to do this. Let us illustrate this method by a simple example. I will leave the details to you, but let us say we have a Boolean formula phi, which is given as follows. This formula is not in 3CNF. It is an arbitrary Boolean formula. It says x1 or x3 ANDed with x4 bar or x7, and this whole thing is once again ANDed with x2 or x5 bar, and this AND is then ORed with x6. So this formula is obviously not in 3CNF. There is no way to recognize clauses in it, and it's an arbitrary formula. We will show that by looking at this formula, we'll be able to construct a new formula that will be in 3CNF, and if this formula is satisfiable, our new constructed formula will be satisfiable. And if this formula is not satisfiable, then our newly constructed formula will not be satisfiable. Firstly, what we can do is, by looking at this formula, we can make what is called a circuit of this formula. Here is a circuit that I made by looking at this formula. As you can see in this circuit, what I've done is used gates, AND gates and OR gates, to denote the AND and OR operation. So by looking at this formula, I can easily make this circuit for this formula. This circuit has an OR gate, and one of the OR gates is being fed by x6, and the other branch of the OR gate is being fed by another complicated circuit which computes something else. So this is how we can convert a Boolean formula, an arbitrary Boolean formula, into a circuit. Let's have a look at the circuit once again. The circuit computes the formula. Now what we can do is, we can go on to the circuit, and you see the wires of each one of these. In this circuit, there are various wires that are running around, and what we can do is, we can label each wire with a Boolean variable. So let's label this wire with Boolean variables, and now we look at the circuit again. So what we have done is used y's to label the wires of this Boolean circuits. So now let's zoom in into this circuit, and let's concentrate on one of the gates in this circuit. And the particular gate now we'll look at happens to be an OR gate. So let's zoom in onto an OR gate of this circuit, and let's see what is happening. So now you're seeing an OR gate on your screen, and it has two wires that are coming into it. One of them is Y1 and the other one is Y2, and the output wire is Y5. So what can you tell me about the values that would be going on this circuit if this circuit were to work properly? What would be the relationship between Y1, Y2 and Y5? Well, since this is an OR gate, y5 would be an OR of y1 and y2. What we want to do is we want to capture this relationship in a Boolean formula. We want to make a Boolean formula which will be satisfiable only by assignments in which y5 is equal to y1 or y2. And remember what we are trying to do. We're trying to make a formula which is in 3CNF. So we want to come up with a formula in conjunctive normal form which doesn't have too many variables in each clause. Let's see how this would be done. Thus, we can write that y true is true if and only if y1 or y2 are true. This is the relationship between y5 and y1 and y2. y5 is going to be true if and only if either y1 is true or y2 is true. We can express this thing in Boolean logic as y5 is equal to y1 or y2. Now, let me tell you how to write down this formula in another way, which is going to be very useful for us. Suppose I write down the formula which is given on your screen as y5 bar or y1 or y2, that's my first clause, and y5 or y1 bar and y5 or y2 bar. Let's think about this clause a little bit. Let's see how these three clauses which are ANDed together, and let's see how we can make this formula true. Let's have a look at it. Suppose that I set y5 equals false. That would automatically make the first clause true. This would mean I have to worry about making the second and the third clause true. Since y5 is false, therefore I must make y1 false to make the second clause true, and I must make y2 false to make the third clause true. So one way to make this clause true is to give all the variables the assignment false. Another way to make this whole formula true is to set y5 equals to true. If I set y5 equals to true, then the second and the third clause are true and I don't need to worry about them, but I have to make the first clause true. Since y5 is true, therefore y5 bar is false, and therefore I must make either y1 true or y2 true. So in summary, the only way to make this formula true is to set all the three variables to be false, or I set y5 to be true and one of the y1 or y to be true. Therefore, we realize that this Boolean formula that I have written on your screen actually is saying that the wires of this OR gate must be set properly in the way an OR gate is supposed to function. So, and if I stare at the formula that was on your screen, it was made out of three clauses. The first clause had three variables and the other two clauses had only two variables in it. Therefore, I can use this to make my formula psi. What I will do is this would be a part of my formula psi, which says that this OR gate in this Boolean circuit works properly. I can play the same trick with an AND gate. Well, what will be the Boolean formula that I will use for an AND gate? Well, I will not do spoon feeding here, and that is your homework. Your homework is to figure out what would be the formula that would simulate or make sure that all the AND gates in this circuit work properly. Once I have these ingredients, then I can actually make one large formula that says all the wires of this, all the gates of this circuit work properly. How would I do that? For every gate, I would make these formulas which are going to be in conjunctive normal form, and each of the clause will have at most 3 literals. If I AND all of those together and AND that with yn, which is going to be the variable which says that the output wire must output a true, then this would mean I'm asking that I'm looking for an assignment that makes this formula phi, the original formula phi, true. So this is our recipe for creating this formula psi. Let's see what we have done in summary. We will write a formula for each wire and all those formulas, and finally we will add the clause y sub m, where y sub m is the output wire of this circuit. So in this example, the formula psi would look like the formula on your screen. As you notice, this formula is a fairly large formula. However, all it is saying is that every gate of this circuit works properly and the output wire outputs a true value. So in short, it's saying that the original formula must be satisfied by the assignment. To satisfy this formula, the output wire must be set to true. To satisfy the formula for the output wires, the two wires feeding from it must be set to true, and so on. Thus, to make psi true, we must make an assignment of the x variables that makes phi true and vice versa. So this is the recipe of the reducibility that takes us from SAT to 3-SAT. Formally, if we want to give the reducibility, if we are given a formula phi, we can construct psi such that phi is satisfiable if and only if psi is satisfiable. The second thing we notice is psi is in C and F. The third thing we notice is that in psi, every clause has at most 3 literals. So psi is a formula that is very close to a 3-SAT. In the next lecture, we would look at how to convert this formula psi into a formula in which every clause has exactly 3 literals, thereby proving that 3-SAT is also NP complete. I'll see you in the next lecture. Thank you and goodbye.